It's the final lab. Let's go. So, did this man over here violate the energy principle? Boom, he goes back up. Bam, he goes up. But why is that hard to believe? Well, we know that not all collisions are fully elastic. There is some internal energy, and in an inelastic collision, which happens mostly in real life, then we have that the internal energy is not equal to zero. So how could the man come back if energy is lost to sound and heat? And my hypothesis is that he did, just not a lot. We have to go through the video quickly, so here's a quick rundown without any equations. Constant motion is enacted upon, that's momentum principle. Energy principle is that no energy is lost, only converted to other forms. And Hooke's principle is that strain and applied stresses is some kind of elasticity. So, spring stuff, you have a constant over some kind of displacement. Now, given that knowledge, just how much energy internal are we talking? And can we find a general ratios for these? Or perhaps a total count? And the answer is yes. Simplifying this man to a few assumptions. First of all, you could put him into a center of mass, so an infinitesimally small ball that's dropped, and it's separated into 4 stages, like the lemur problem in our homework, where you have the falling ball hitting and compressing the spring uncompressing and releasing the ball, and a maximum height. Now here's the assumptions again. The trampoline is a spring. He could be simplified to a center mass. It has a close enough body weight to the average US male, 88.7 kilograms, and for tracker displacement, the spring compression is 0.133 meters. So the time to hit the trampoline from the video is 0.9 seconds, and given a momentum principle where distance is equal to 1/2 acceleration times t squared, well, since we have no initial velocity and initial position is 0, then we could say that d is equal to negative 3.97 meters. Hence why the calibration stick, if you guys could see it, is negative 3.97. Velocity upon hitting a trampoline is going to be negative 8.82 meters per second. This is because it's acceleration times delta t. And since our initial velocity is equal to 0, well, that's why we didn't include it in this formula. And that's the momentum principle for anyone wondering. Impulse could be expressed as its momentum, or force times time of contact, as per the momentum principle. So we say that mass times the final velocity, which we found earlier from assumptions and from the video, is equal to negative 782.33 kilograms times meters per second. Given that impulse also equals force times the time of contact, so we could rearrange our k from the spring of force to find that it's about 6,500 Newton meters squared. Now, let's go ahead and rework our equations. So we know that we have kinetic energy translation plus potential energy internal from our point mass system, and that we have mass times gravity and some differences in height from our work surroundings. So, from our energy principles, we say that since the kinetic energy is equal to 0 because initial and final velocities were 0, given their height differences was about negative 1.2 meters, then we get a total answer of about 1040 joules in the internal potential energy, satisfying an earlier question of what is the total potential energy, or energy lost, if you will. So let's code and just find out how much we lost in the real model compared to theoretical. Here the spring constant is different, because in the video that we're doing right now, we assume that he was an average weight, but perhaps that's not true, or perhaps the fish lens of the camera that we used was also not true as well, so might have caused some error. In any case, we also have that there, and if we did it correct for k, when we use original values, it's quite off. Now, in the first stage, gravity is the only component. This is because there's no spring on it, and we have the position update formula from Newton's second law as well on the bottom. In the second stage, gravity and the spring are active, along with the third stage. In the fourth stage, only gravity is there. Ignore the and spring part on the end there. With a corrected k, we have a conserved energy state as such. And here we're going to quote-unquote vibe check reality. Here are some discrepancies between the real and theoretical models. The bad video causes a dip and some discrepancies, as seen on the left. In the middle text box, we see that the energy internal, though, still detracts from kinetic energy, leading to lower spring force. Or, well, supposedly, at least. And on the right, we see that energy internal is about 1000 joules. Subtract the heights from 1.2 meters from our theoretical. And thus we could tell that since our theoretical was a perfect sum condition where we didn't quote-unquote lose energy, then we could see that yes, there is some internal energy enacting on our system that has caused this difference, whether it's from friction, sailboats, whatever. Now, does this data make sense? And the answer is yes. If his center of mass was about 1 meter tall, and he jumped about 0.8 meters, and the height loss was about 1.2 meters from original, then that leaves us about 2 feet above the ground. And in the video, his buttocks was barely hovering above the ramp, indicating his prediction for loss of energy is close enough to accurate. That looks like a pretty heavy dump of energy, as seen from a graphic. So basically, the energy principle is not violated. Energy was simply put into different forms of friction, heat, sound, and etc. You get about a half-meter difference from the ground, hence why he had to crouch to get back up. Whereas most energy loss... Excuse me, I'm sick today. Stages 1 and 4, which are the ones where you mainly have the air resisting against it, is proportional to force of drag, which is independent of mass. However, and since 2 and 3 are proportional to mass, since that's with heat and friction losses, which is proportional to normal force, which is proportional to mass, we can say that most energy internal was lost in contact with the trampoline. Thus we solved all questions of ratios, what the total energy was, and hopefully you learned something today.